The last thing we're going to do is use the formalism of residues to give a proof of the Lagrange inversion formula, which we stated before but didn't prove it. So what did it say? I'll take f analytic near 0, and I want its derivative to be non-zero. And another way to say that is I can factor out, well, I'm assuming its value at 0 is 0, in which case I can factor out a z and write it as z over phi of z. And you have to kind of get it into this special form in order to state Lagrange inversion in the simplest way possible. And so because the derivative is non-zero, you get phi of 0 is non-zero. And if the derivative is non-zero, it's locally invertible, so I'll have an f inverse that has a power series representation. And the Lagrange inversion formula says that the nth coefficient of f inverse is 1 over n times the coefficient of z to the n minus 1 in the power series for phi to the n. So it's definitely a complicated thing, but we can state it somewhat efficiently in this form. If you attempted to do this without writing f first in this form, it would be even worse. Okay, so we had a homework exercise, which was to show that if a function is defined on a punctured disk around the origin, if it's analytic, and if it has an antiderivative on the whole domain, then its residue at 0 is 0. And we're going to use this below to help us prove Lagrange inversion. Well, we're really going to use it to help us prove this lemma. So here's the main lemma that we'll use. It's sort of a change of variables for residues. And we'll have other ways to kind of explain this formula later, but we can prove it directly right now. So assume F is analytic, assume G is analytic on a punctured disk. And then suppose we have F mapping some small disk to some other into some smaller disk, and assume it's injective. So we also have F prime of 0 is non-zero. Then the residue of G at 0 is the residue of G composed with F times F prime at 0. So it turns out we can prove the Lagrange inversion formula pretty easily with this lemma, so let's do that, and then we'll get back to the proof of the lemma. Let's see, so here's the lemma we're going to use. Here's Lagrange inversion, and here's my proof. Okay, proof of Lagrange inversion, assuming this lemma. Okay, so I have F inverse written as this power series, and we know it exists already because we had a inverse function theorem for analytic functions. Okay, so it actually helps to work with its derivative. So the derivative of F inverse, I can write its power series like so, and we already saw that I can extract coefficients using residues. So the residue of F inverse prime of z to the minus n will give me the coefficient of n minus 1 in the above power series, which is n times bn. Okay, so that's closely related to this in the formula. Now we're going to do some tricks, so it isn't totally obvious that this is what you should do, but let's see how it goes. F inverse composed with F is just Z, right? Because they're inverses. If I take the derivative of this formula, I'll get F inverse prime with F plugged in times the derivative gives me 1. Okay, and now I'm going to use the lemma with the change of variables where I'm plugging f in. And I didn't really need to write f as z over phi until the very end, but I'm doing it anyway. Okay, so I'll use this change of variables formula here, and this is a little subtle. I'm going to plug f into this function and then multiply by f prime as in the formula here. So I'll plug f into it. So that's plugging f into the first function and into the z to the minus n term. And then I have to multiply by the derivative in this kind of change of variables residue formula. But I already said that this piece times this derivative gives me 1 because f and f inverse are inverses. And then you're only left with this term here, which is phi to the n, z to the minus n, which gives me the z to the n minus 1 coefficient of phi to the n. And this was equal to n bn, and that's exactly what we wanted to show up here. Okay, so that's the proof of the theorem, assuming the lemma. The lemma is actually a little tricky to show, but let's see how it goes. Okay, so let's recap the lemma. I have G, analytic on a punctured disk, and then an injective function, and I want to see how the residue changes when I plug F into it, essentially. Okay, so G is analytic on the punctured disk, so it will have some Laurent series expansion. And again, its residue is just the B minus 1 coefficient. And if I plug F in here and multiply by F prime, I get this series. And I'll leave out some details here, but you can show that this converges absolutely and uniformly on sort of sub-annuli. Okay, and I want to show that the residue of this at 0 is just the residue of G at 0. So to compute its residue, I'll integrate it around a small circle. And because this converges absolutely, I'll be able, and you can actually, bound the elements by constants that converge absolutely in order to pull the sum outside the integral. We can talk more about that if you like. I can pull the sum outside, and I'll just get the bn's, and I'm just integrating around this circle around the origin, so I'll just get the residues of f to the n f prime at 0. Okay, and now is when I want to use this exercise. Let's put it over here. Most of these residues aren't going to do anything. In fact, all of them except one aren't going to do anything because f to the n f prime has an antiderivative when n is not minus 1. Because I can just write the antiderivative is f to the n plus 1 over n plus 1. So the residues of all of these terms when n is not minus 1 will be 0. So I can forget about all of this except for n equals minus 1. So the residue I'm after here, I'll have the coefficient b minus 1 times the residue of just the case n equals minus 1, which corresponds to f prime over f. And I claim this residue equals 1. You can just get that f vanishes at 0 and is injective, so I can write it this way, where h of 0 is non-zero. And briefly, f prime over f, you can expand this derivative into 1 over z plus h prime over h, and this part will be analytic at 0 because h is non-zero at 0. So the residue is the coefficient of 1 over z, which is 1. So this is just 1. So this residue equals this residue, and that's what we needed to prove the Lagrange inversion theorem.